Good morning. This is your course on linear integrated circuits unit 3, and today's topic is instrumentation amplifier. What is instrumentation amplifier? So we have seen in last classes about operational amplifiers and its applications like inverting, non-inverting, summing, differentiation, integration and many. In this class, it is another application of operational amplifier called instrumentation amplifier. What is instrumentation amplifier? It's a special kind of operational amplifier. It's also a type of differential amplifier with some input buffer amplifiers. So in this tutorial, we'll learn about a few important instrumentation amplifiers basics and application, and also the circuit and working of 3 op-amp instrumentation amplifier. So before that, you should know about the difference between the differential amplifier or the difference amplifier and the instrumentation amplifier. Actually, it is both are same, because difference amplifiers are being used in instrumentation amplifiers. Okay, so what is the difference is that the instrumentation amplifier is one type of differential amplifier. The instrumentation amplifier can be built with 3 operational amplifiers. Okay, the differential amplifiers can be built with only single operational amplifiers, and the output voltage of difference amplifiers get affected because of the mismatch resistors. But in the instrumentation amplifier, it will offer gains with only a single resistor of its primary phase that will not affect the resistor matching. Okay, so ஒன்றும் ஒரு differential amplifier அப்படின்னா it gives the difference between the two signals. Okay, so what is the disadvantage in difference amplifier is that it will not allow very low signals. Okay, it cannot pass very low signals, or it cannot amplify very low signals. But instrumentation amplifier has a property of amplifying, okay, and allowing very low weak signals too. So in the field of medical fields and many other fields where you want to amplify the weak signals, so that is the main advantage compared to the differential amplifier with respect to instrumentation amplifier. So what are the requirements of a good instrumentation amplifiers? Okay, it has a finite, accurate and stable gain. It is easily the gain can be adjusted. It has high input impedance. It has low output impedance. It has high common mode rejection ratio, and it has high slew rate. Okay, so as common, the gain can be easily adjusted. Okay, as of not in differential amplifier, the instrumentation amplifier's gain can be easily adjusted, and the common mode rejection ratio is higher. So if common mode rejection ratio is higher, you can easily reject the common mode signals. So what is a common mode signals? The signals that is unwanted in the output, like noise. So since its common mode is high, it can reject the almost all the unwanted signals like noise. So this is your circuit design of a 3 op-amp instrumentation amplifier. This is your input circuit and this is your output circuit, or input part or output part. So commonly it has 3 operational amplifiers. In input side it has 2 operational amplifiers, and in output side has 1 differential amplifier. This one operational amplifier 1 and operational amplifier 2 will act like a voltage follower, and this is a difference amplifier. Okay, so voltage follower is nothing but whatever the input you will give in the circuit, the output will be same. So the voltage will be followed in both the input and the output. Now that is why it is named as voltage follower. So what is a difference amplifier? It will give the difference of the 2 input signals, amplified and rejected with common mode. The output will be amplified and rejected common mode signals like noise. Okay, see, in this input side you have one operational amplifier, and that has been given input with the non-inverting terminal in both the operational amplifiers. So it is connected with the resistor 1, resistor R gain in both the op amps. Then the output is taken from the operational amplifier 1 and given to the inverting terminal of the op amp, and the output of the op amp 2 is connected to the non-inverting terminal of the op amp 3, and the difference of this two op amp inputs is taken as the output. Okay, it is just like a difference amplifier, except that the input is not directly given to the difference amplifiers, but it is given first to your voltage follower, and there some signals are being rejected, unwanted signals, and then it is given to the difference amplifiers with the help of resistors. So the R gain is going to play a major role here. The R gain is a variable resistor where you can vary the resistor to adjust the gain of the amplifier. So we know that the gain of the amplifier is that going to amplify the gain input signals, amplify the low level signals to the signal that is wanted in my output part. Okay, so this R gain is going to play the major role here. So we have seen about the circuit design of the three op amp instrumentation amplifiers. So the op amp 1 and 2 are non-inverting amplifiers and together form an input stage of the instrumentation amplifier. The op amp 3 is the difference amplifier that forms the output stage of the instrumentation amplifier. So now we will see the working of instrumentation amplifier. So first we will take the input part and we'll derive what is the V01 and V02, and finally we'll derive the output part. Okay. The output stage of the amplifier is, as said, it's a difference amplifier. So the output of the difference amplifier is already been derived in earlier classes. So what is the output of the difference amplifier? It is the RF, that is feedback resistor, divided by the R1 into the difference of the output. So since here it is R3 is your see in this R3 is a feedback resistor, and divided by the input R2 resistor, input resistor R2, and into the difference of the two inputs. So the output of the second part, that is output stage of the instrumentation amplifier, you will have output as V output is equal to R3 divided by R2 into V01 minus V02. So this V01 minus V02 is going to be the output that is from the input stage of the amplifier. So see here V01 is the output from the amplifier 1 and V02 is the output from the amplifier 2, and this will be taken as an input to your difference amplifier in the output stage of the instrumentation amplifier. So now we have to derive this, what is the V01 and V02, and then substitute in this Vout value and get the output of the instrumentation amplifier. Okay, so Vout is equal to, okay, from the figure. Okay, so see here the expression for the V01 and V02 can be found in terms of input voltages and resistance. Consider the input stage of the instrumentation amplifier as shown in the figure. Okay, so Vout will be R3 by R2 into 2R1 plus R gain divided by the R gain into V1 minus V2. So now we have to bring this output value. So let us derive them. So see here, ideally the current to the input stage of op amp is 0. So this is the golden rule we should remember. Ideally the output of the instrumentation amplifier is 0 Okay, input of the operational amplifier is always considered as 0. Okay, remember this. So I is equal to, apply Ohm's law, okay, between this E and F. Okay, so I is equal to V naught, so difference, okay, we are going to apply Ohm's law. I is equal to V by R. So V here is V naught 1, the difference in the voltages, V naught 1 minus V naught 2 divided by the number of resistors. So R1 plus R gain plus R1. So you can write it as I is equal to V naught 1 minus V naught 2 divided by 2 R1 plus R gain, because we have 2 R1, so it is added. Okay, then since no current is flowing to the input of the op-amp 1 and 2, the current I between the nodes G and H can be given as. So where is G and H? So this is your G and H. So now you have to write the equation for current equation for this nodes, between these nodes. So G and H. So what is the flowing voltage will be? Vg minus Vh. The voltages will be Vg and Vh divided by the R gain. So now you can equate the equation 1 and 2, okay, because the current flow is 0. It's common. So on equating you will get equation like this: V naught 1 minus V naught 2 divided by 2R1 plus R gain, that is equal to V1 minus V2 divided by the R gain. So now you can find the value of V naught 1 minus V naught 2, and you have to substitute in the equation we have derived for the difference amplifier, that is output stage of the amplifier. The output of the difference amplifier is given as V out is equal to R3 by R2 and V naught minus V naught 1 minus V naught 2, and you have to substitute this V naught, this equation 3 here. Okay, therefore we'll get the output value as such. Okay, so that is the derivation for the instrumentation amplifier, which has 2 stages of 3 operational amplifier. Okay. So next is your advantage of 3 op-amp instrumentation amplifier. The gain of the instrumentation amplifier circuit can be easily varied and controlled. The gain of the amplifier depends only on the external resistors used. The input impedance of the instrumentation amplifier is dependent on the non-inverting amplifier circuit in the input stage. The input impedance of the non-inverting amplifier will be high. The output impedance of the instrumentation amplifier is the output impedance of the difference amplifier, which is very low. The CMMR of op-amp 3 is very high, and almost all the common mode signals will be rejected. So see the advantage. The gain of the instrumentation amplifier is easily varied by R gain, external resistor R gain. Okay, then the input impedance of the instrumentation amplifier is dependent on non-inverting amplifier circuit in the input stage, and that input impedance is also very high. Okay, input impedance is also very high, and that most important is all the common mode signals mostly will be rejected. Okay, the CMMR of third op-amp is very high, and almost all common mode signals will be rejected. So see some applications of instrumentation amplifiers. So it is used in transducers like thermocouple, strain gauge, Wheatstone bridge, measurements of etc. Okay, other transducers. So what is a transducer? Is that it will convert physical quantities into electrical quantity. So wherever you have to convert like pressure, temperature, light intensity into electrical signals. So here that type of working, this instrumentation amplifier is very much used. So where you have to amplify the electrical signals from the transducer, which is very weak, to some amplified value and given into the display of some applications. So these amplifiers are used in navigations, medicals, radars. Okay, these amplifiers are used for imaging as well as video data acquisitions, the high speed signals, and these amplifiers are also used in radio frequency cables. Okay, so it has a wide range of applications. So instrumentation amplifier is a very important amplifier that is mostly in all applications where you want to amplify the weak signals. These instrumentation amplifier has been used. Okay, so thank you. We'll see the next class some applications of instrumentation amplifier in detail. Thank you, ma.